do this problem regarding this. So a rigid tank with a volume of 1800 liters. So let's just try to put this. So a rigid tank, okay, no displacement, no cylinder piston, and it has a volume. I'm going to put volume 1 of 1.8 cubic meters. I'm just already converting units. Contains steam at, okay, let's just put T1 to 20 degrees Celsius. Great. The fraction volume, oh, okay, there's something weird here. Let's just see. The fraction of volume Y1 is a fraction, so there's a fraction of what? A fraction of volume in liquid phase. Okay, so right from the start, I'm gonna know that this is a mixture. So if they are telling you that this is a mixture, because there's gonna be a part in liquid phase and a part in vapor phase. It doesn't say this data, okay? So I'm gonna pick it. That's what I do when I need to leave open something and then do several problems just out of several data. So what I'm going to do in this case, so I'm going to say that the y1 equals to 2/3, okay? That means that 1 minus y1 equals to 1/3. This is equal, according to the problem, equal to the volume of the liquid phase divided by the volume of the whole rigid tank. And this one is going to be the phase in the phase of vapor divided by the volume of the whole rigid tank. Okay, so that's what is going on. Okay, I know this number, therefore I'm gonna be able to get all of these guys. I'm gonna do it right now. Okay, so the volume of the liquid phase at 1 equals to 1.2 cubic meters. Meanwhile, the VG1, the volume of the gas phase, this thing occupies cubic meters. So maybe you can see that here you have 0.6 of vapor phase and 1.2 of liquid. So that's how this thing is occupying the whole volume. Great. Now that I have that, I still haven't read anything, but I know that I have a lot of data just from the start, okay? The rest is in vapor phase. Well, that was something. Thank you for clarifying that, but we already knew that. Find the pressure inside the tank. Okay, that one is easy. I already know that this thing is a mixture. So if it's already a mixture and I know another data like the temperature, I'm gonna be able to find the pressure. So I'm gonna go back to this table and look at the fourth row. So the fourth row, maybe you can see, I'm gonna try to increase it. Now you see to the 220 degrees Celsius, and right at the right, you will see the saturation pressure. This thing is boiling. Therefore, P1 equals to Psat, if you want to put every information there, at T1. So this, in this case, P1 equals to 2,319.6 kilopascals. So that's my answer A. Okay, so this is my answer A. Now, the quality of the mixture, great. It's a good question. And maybe you will be lured in order to say, well, you know what? I already have the liquid phase and I have the total phase. So I'm just going to do this division. And I'm going to write wrongly that x1 equals to 2/3. I'm sorry, not 2/3, because it should be the 1/3. Because maybe you think that if I use the volume of the gas phase divided by the total volume, that is the quality. It is not. This is wrong, okay? So I'm not going to leave it there. So this is wrong because the quality is calculated with mass. So I'm going to put here x1 equals to the mass of the gas phase at 1 divided by the total mass. And the way to get it, it's kind of simple. This is what I would do. I would say, well, you know what? I'm going to take that BF1 equals to the BF1 divided by MF1. That's one way to call the specific volume of the liquid phase. And this is BG1 equals to BG1 divided by the mass of the gas phase at 1, okay? So this one I already have it. This one I already have it. This one I can get it from the tables. It's right at your right. It's actually this. Let me just put it for you. So this one is exactly this one. So at 220, I have BF1 and I have BG1. Okay, so those are my values. So I'm going to write them in order to waste you a little bit of time. But the thing, well, I'm not going to write them. You already know them. You can write it by yourself. So I'm going to save a little bit more of time. And then what I'm going to do is just to calculate if I can move this thing around. Okay, saying thank you. So this one is known and this one is known. It's right at your right. Therefore, the MF1, you can get it. So that's what I'm going to get. So the MF1 is going to be equal. I'm going to put the numbers for this one, but the other ones, I'm not going to put them. So MF1 equals to, this is 1.2. That's the liquid part. This one is the liquid part divided by the value of 0.00119, okay? And mg1 equals to 0.6 divided by 0.08694. Okay, so with this, I already have these numbers here. So mf1 equals to, hopefully I have them in the right way. You can also say, well, you know what, those are not the ones that we're looking for. And you should check. You should always check if what I'm doing here is correct. And then I'm going to put the mass part, and the mass part is 6.969 kilograms. Okay, so these are my masses of each phase. And then I'm going to get M1, which is the adding up both phases. And if I add them up, I will have that the total mass is 1,015.4 kilograms, which is a huge deal of water. Okay, so this is M1. I still haven't got what I was looking for, but this is now pretty straightforward. X1 equals to the 6.969 divided by the 1,015.4. And with this value, I will have a really small value. This equals to, if I have this right, is 6.863. And then I'm going to make myself a little bit of room. 10 to the minus 3. So it's a really small quantity, 0.0068. Actually, the relationship between gas phase and the total phase, the total phase or total mass. Okay, so what I'm gonna do here is erase this one. Great. So now I have the quality. I have the quality, and that's what they were asking me at B. So this is, oops, this is B. Great. Now let's just see what they're asking. The density of the mixture. So the density of the mixture, C, I'm going to put it right away, equals rho 1 equals to 1 divided by V1. I haven't calculated V1. If you want to know how to calculate V1, it's going to be equal to BF1 plus X1 multiplied by BG1 minus BF1. And I have everything. I have everything now. And I actually can calculate it, but since I don't need it, maybe I'm going to need it later, and I want to say, oh, I should have calculated it. But so far, I also can do this one. If you know the definition of density, it needs to be the total mass divided by the total volume, and I have both of them, so it's 1,015.4 divided by the volume, 1.8. And if you do this calculation, so the density of at one is going to be equals to 564.046 kilogram per cubic meters. Great. Now I already have what it's C. This one is C. Now let's just go what else. Okay, now something happens to this one, and I'm going to put here, this was initial state, and I'm going to put it here too. So something happened to this initial state, still the rigid tank, but now let's just see what conditions have changed. Okay, now the tank is being heated. Okay, so there is introduction of heat. I need to, well, believe that it's happening until the pressure is 3 megapascals. Okay, so I'm going to put here P2 equals to 3 megapascals. I'm going to believe that. And I'm also going to say right away that B2 equals to B3. I'm sorry, what 3? This is not 3, but this is B2 equals to B1. And I don't have V1. Oh my God, I should have calculated this one, okay? And you can say, well, you know what? You can put this one, total volume equals to 1.8 cubic meters, because this is what you have at first part. Well, it's not a bad idea, but the thing is that we actually need specific volumes in order to go into the tables. Total volume doesn't help us a lot, but nonetheless, V1 equals to V1 divided by the total mass. And I can put 1.8 divided by 1,015.4, which is, if you want to know, the inverse of the density. Well, okay, so this value, I think I have it here. Hopefully I have it here. This one is 1.77, and then 2 to 10 to the minus 3. Yeah, 10 to the minus 3 cubic meters per kilogram. Got it. Great. So I'm going to make myself a little bit of room. I already have that part, okay? They are not asking me that. I don't know what they're asking me. I'm just following instructions, okay? And then now that it's at 2, and this thing is at 3 megapascals with the same volume that 1, okay? Please give me the heat supplied and the work and its direction. Okay, so I'm gonna do E first, so the work part. The work part equals to 0, okay? That's pretty simple. Why? Because this is a rigid tank, so I will not care too much about that. But for the D part, I need to put this. So D, delta U equals to Q minus W. If you're gonna follow this sign convention, this one is 0. Therefore, I need to calculate delta U if I wanna get Q, okay? Oh, okay, so the only way to calculate this Q is to do M, the total mass. That thing won't change. U2 minus U1 that comes from tables. Okay, so let's just put Q. Let me just see, and I see that at 1, I never calculated U1, but now you can do it. So let's just start doing it. So U1 equals to UF1, because it's a mixture, plus X1 multiplied by UG1 minus UF1. Okay, so using the table, you can go and see where were we. So 220, yeah, it's 220. And maybe now you can, if I can do it, yeah, so this is your 220, yeah, 220. This is the value for your UF1, and this one is your value for UG1. Okay, so you need to tell me when you're doing this type of problems, you need to explain to me a little bit, okay? You need to explain to me that UF1 and UG1 are calculated at T equal to 220 degrees Celsius. Otherwise, I need to know what's going on. Okay. Okay. So now I'm telling you what's going on. And I think I have this thing over here. Let me just write in. Oh, it's at the right? So 940.79, and then UG1 equals to 2010.3. And let's do this story a little bit shorter. So U1 is gonna be equal to 952.11, no, not 11, but 18.7 kilojoules kilogram. You need to check if this thing is correct or not. So I haven't found yet the heat supplied, but nonetheless, I have a piece of the puzzle. Now let's just go at 2. And at 2, I still don't know where am I. I still don't know if this thing is a mixture or not. I went back, to calculate U1, but I haven't done anything at 2. So let's just find out what do we have at 2. And I'm going to do it with another color. Let me just erase this stuff. And what I have here, let me just see if I can change color. Yeah. So at 2, my data at 2 is 3 megapascals, 2. And I have B2 equals to 1.772 10 to the minus 3. So that's what I have. So I'm going to check where the hell that is. So I'm going to move myself into this table, and instead of using the temperature table, I'm going to use the pressure table. And the pressure table, I'm going to go to 3 megapascals. So that is 3,000 kilopascals. And I need to check both values, these both values for BF and BG. And maybe I can put it here. Maybe you can see just using your eyes that this 1.77 is actually 0.0017, okay? So this is your lowest value, and this is 0.0012. So this one B2 is 0.00177. So it's going to be higher than the saturated liquid specific volume. Okay, so this one over here, I'm going to write it here. So this one is already a mixture. Just by looking at the table, it's mixture. Because this one, I'm going to put it here, BF2 equals to 0.001217. Meanwhile, BG2 equals to 0.06667. Okay, and then now that I'm there, I'm going to write UF2 and UG2, because maybe I'm going to need them in order to calculate U2. So those values, right, if I can see them here, are 1004.6 and 2603.2. Okay, so I already have those numbers. in order to calculate something. So if it's a mixture, you should always get the quality. So let's just get the quality. So x2, you cannot say that it's the same quality that you had at 1. It can change, okay? It can change. The only thing that didn't change was the volume, but everything else can change. So you always need to check. So x2 is going to be equal to b2, which is the data that I have, and then bf2, and then divided by bg2 minus bf2. And if you do this, therefore x2, I already have it here, is going to be equal to 8.49 10 to the minus 3. Okay, so this is the value of the quality at 2. And maybe you can check now values of qualities. So this one is 8.00849. Okay, so this is the same 0.00849. And then let me just go to this other one. And this other one was, if you want to put it in another way, 0.0068. So the quality increased very, very little, but it increased. Okay, well, okay. So I'm going to follow that line, and then I'm going to calculate stuff. So with this known value of x2, I can get right away u2. This is uf2 plus x2 multiplied by ug2 minus uf2. And I can put everything inside of that, and I already have the number. So u2 equals to 10,000 not, but 1009.6 kilojoules kilogram. Okay, so that's what I have. Now, if you want to calculate heat, I'm going to write it again. Delta U equals to Q. This is that M U2 minus U1 equals to Q. Okay, so I can put this one in, and this one I already have it from the start. This is the total mass. This was M1, which is exactly the same as M2. Okay, so if you do that, you will find yourself 1015.4 kilograms, okay, multiplied by these numbers, 1009.6, and the other one was minus 952.187. Okay, so the value of this one, this is Q, of course, so Q is going to be equals to, this is what I have. You should check this one out. 58,297.16 kilojoules, which is a huge deal of heat. Okay, it's a big, really big quantity, and that's because you are using almost a ton of water, or really a higher value than a ton of water. Okay, so that's it, guys. I will see you later.